But welcome to the next session on electrochemical cells. We've gone through a series of sessions dealing with galvanic. In this case, we want to deal with electrolytic cell. I want us to deal with electrolytic cell. Electrolytic cell. Electrolytic cell coming from the word electrolysis. Electrolysis. All right? Electrolysis. And electro simply coming from the word electrical energy. Electrical energy. While the word lysis is a Greek word meaning to break up. So in this case, we are actually using electrical energy to break up chemical energy, a chemical substance. So in simple terms, we are dealing with the conversion of energy from electrical to chemical. In galvanic, we said we're moving from chemical to electrical. So an electrolytic cell, therefore, is an electrochemical cell. Remember, we said electrochemical cells are devices. All right, electrochemical cell that converts electrical energy to chemical energy. So we're converting electrical energy, and this should automatically tell us something here. Since we are using electrical energy, we therefore need a power supply. And ideally, we always use a DC. DC meaning a direct current supply. I know some of you are asking why specifically a DC, direct current supply, because we want to maintain polarity. We want to maintain polarity of the electrodes. That is, we keep the anode as the anode, and we keep the cathode as the cathode. If we use the AC, it keeps changing. Hence, we have oxidation and reduction taking place at both cells simultaneously and interchanging, which definitely would disturb the whole setup. So the anode remains the half cell where oxidation takes place. Again, anode, oxidation will always take place at the anode. Oxidation, which is the loss of electron, and you have the cathode where reduction takes place. Now, since we are using electrical energy to drive the system, it means this system is not spontaneous. Remember, we were getting a positive value, saying it's exothermic. Now, this system is not spontaneous because we are using electrical energy to drive the system. Now, so electrolysis, therefore, is a process where we use electrical energy to break up a chemical substance. We would see all that in just a while, but we need to get these definitions out of the way in building a foundation for our proper understanding. So we need to know what electrolysis is, the process where electrical energy is converted to chemical energy. And let's put that down as well. Electrolysis now is a process where electrical energy is converted to chemical. The other one we were doing was chemical to electrical, but this is electrical back into chemical. We do have our half cells, again the cathode and the anode. The difference here is we have a power supply, while on the other one we do not have a power supply. Here we do not need a salt bridge, but in a galvanic we need a salt bridge. So those are a few differences between the galvanic and electrolytic. No salt bridge on this. There is a power supply, which is a DC power supply on this. Let's look at what a typical example of. Now, in this case, we could actually have them in one particular cell. All right, so I'm going to have my electrodes. I'm sure we remember what electrodes are, and these are, these electrodes are connected to a DC supply. The diagram already is different, and what we have here is our electrolyte, which we said is an ionic compound, an ionic solution. It must be a solution. Electrolyte, it must be a solution. It cannot be a solid. Electrolyte, it's an ionic compound, ionic solution, all right, that allows the movement of ions. Most of the time we use salts. An example of salt, like we mentioned, you have your chloride, you have your nitrate, and you have your sulfate. These are examples: chloride, nitrate, and sulfate. All right, this is the positive terminal and this is the negative. So this electrode will be our positive electrode, and this electrode will be our negative electrode. Now, in the galvanic cell, we said the cathode is the positive. In this case, the cathode becomes the negative. The cathode becomes the negative, and our anode becomes the positive. But remember, oxidation is still going to take place here, and here we're going to have reduction taking place. Oxidation still maintains its definition as the loss of electron, oil rig, while we have the reduction as gain of electron. Okay, now it's a simple process in the electrolytic cell. Quite simple. The process is just the same all through. I'll give us a list of the process just now, and then we'll look at different applications and run into the cell. All right, the first thing that needs to happen with an electrolytic cell is that the electrolyte, remember we said we are breaking it up, the electrolyte will break up. And when it breaks up, we have our positive ions, cations, and negative ions. All right? So we have these positive ions and negative ions. For example, if we have copper chloride, what would happen? It will break up. We have Cu, we have Cu2+, and we have Cl-. That's an example. That's a breakup. All right, we use electrical energy to drive the breaking. If we have copper sulfate, for example, what are we going to have? we have copper sulfate, we have copper there, and you have your sulfate ions. If you have your zinc chloride, again, you have your zinc 2 plus, and you have your Cl minus. So all these are ionic compounds because there must be transfer of electrons. Again, what other thing could we have? We could have your zinc sulfate as well. And what do we have? You have your zinc 2 plus, and you have your SO4 2 minus. The same way. Even if you have a nitrate, you are going to have your nitrate, and then you have your metal, which is going to be the cation when the nitrate becomes the negative ion. All right, so we have all this splitting. But remember that we do have a positive electrode, and we have, okay, let me do that here. We have a positive electrode, and we have a negative electrode. Now, when this splits up, let me use this as an example. We know that charges, unlike charges, are going to attract. So automatically what will happen is the zinc 2 plus are attracted towards the negative electrode. And remember, the negative is the cathode. So they are attracted towards that, and that's where reduction takes place, while these ones are attracted towards the positive ions, and that's where oxidation takes place. So it's a simple process like that, but we would see some variations here and there, but the process remains the same. The first process is that the electrolyte would break up into its constituent ions, cations and anions, and then we have the migration of ions, and then we have our redox reaction taking place. Okay, now a few applications that we would quickly look at would be, number one, it's the electrolysis of copper 2 chloride. Let's start with the first one. Electrolysis of copper 2 chloride, copper chloride, CuCl2. Like we said, and I need us to know this one could change, but I would help us see what will happen right now with the process, copper 2 chloride. Let's have a diagram. I'm going to repeat that diagram for clarity. CuCl2. We've not mentioned our electrodes, and that I'm going to mention just now. All right, we have this. Remember, this is the anode, and this is the cathode there. And we have our CuCl2. When this breaks up, remember what we have. We have our Cu2 plus, and we have our Cl minus. Remember that the characteristic, okay, we should use blue here just to help us. The characteristic color of Cu2 plus, it's blue. All right, this is blue. The more Cu2 plus ion you have in the solution, the more blue substance, or the more blue color we would have, because CuCl2 simply is characterized by blue. All right, now this system operating, remember, it's a DC supply, it's non-spontaneous. What will happen? Okay, let's talk about the electrode. I'm going to do two different setups here. In the first setup, let's call this setup A, we are using copper electrodes because we're dealing with copper, CuCl2. Let's use copper electrodes. Now let's see what's going to happen. First, we have a breakdown, and secondly, what do we have? We have a migration. This Cu2 plus will move towards the negative electrode because of the charges. The positive ions are attracted towards the negative electrode, while the chloride ions, Cl, are attracted towards the positive. So we have a migration there of ions just due to the charges. Now the question is, what happens at these electrodes? Let's see, at the anode. All right, let me just draw the anode quickly. Remember, it is positive, and we have what? Cl minus attracted towards that. Okay, remember that this is copper electrode. All right, copper electrode. Now, so the negative charge ions are already at their position. But now let's check something. We have Cu here, and we have Cl. We have Cu and we have Cl. There's going to be either oxidation of one of the two, either Cu or Cl. Let's check something on our table quickly. Let's check our table. Let's find chlorine. Let's find, already we know copper. We've been dealing with copper all along. Let's find chlorine. Now, if we find chlorine here is positive 1,36, while our copper, remember we've got two of them right now at the same position, 0,34 and 1,36. Let's go back there. We have 0,34. This one is 0,34 positive, all right? And this is positive 1,36. Let's make sure we have the right value, positive 1,36. All right. Now that we have two, but remember that at the anode, oxidation takes place. So with our knowledge, the more positive one will be reduced. So this one will be reduced, while this one will be oxidized. But remember that at the anode, only oxidation can take place. Therefore, our copper, therefore, will be reduced, will be oxidized. Cu will be oxidized. Cu will be oxidized. Remember, because at the anode, oxidation will take place. Oxidation will take place. And what is oxidation? We have Cu changing back into Cu2 plus. All right. So copper, like we said, will be oxidized. And remember what our oxidation half-cell reaction will be? It will be Cu, which is the loss. Okay, so it's going to be Cu2 plus, I need you to watch this closely, because we're going to change the scenario by using a different electrode, and the whole game just changes. But in this case, we're using copper electrodes, and we have copper and chlorine here fighting for oxidation, but we know that the less positive one will be oxidized. So copper will be oxidized, and we have that. So it means this copper is actually now being oxidized into the ionic Cu2 plus. Now, what happens at the cathode? Let's see what's going to happen at the cathode. At the cathode, remember what we have. Again, we have our cathode, being the negative, and we have Cu2 plus. Now this is the only substance here, and we have Cu. So obviously we're going to have a reduction. Cu2 plus, this is reduction. Cu2 plus will be reduced to copper solid, which means we are going to have, this is in an ionic state, while this is a solid state. We would have Cu beginning to appear here, the solid material beginning to appear on this electrode. This will definitely mean an increase in mass. An increase in mass of that, while on this other one, because this guy is dissolving into Cu2 plus, it's going to be a decrease in mass. So these are things that happen simultaneously in our electrolytic cell. So there's a decrease in mass there, there's an increase in mass here. What's going to happen to our electrolyte? I want to quickly see something very beautiful here. You have Cu2 plus, you've got this, and you've got that, anode and cathode. Now, remember that this migrates towards the negative electrode, while from the positive electrode we have Cu2 plus going into the solution as this one leaves. So basically there is a replacement. For every Cu2 plus lost, there is another one replacing. So the concentration here does not change. The concentration of CuCl2, whether CuCl2, whether CuSO4, does not change, which means the blue color remains the same. The grade of the blue color in this particular setup will remain the same. What if we change the scenario? And I want us to carefully understand what will happen if we change the scenario. And what do I mean by changing the scenario? We have the same electrolyte, but now I want to change my electrodes and have graphite electrodes. Here we have carbon now. Am I right? Carbon, so we don't confuse the C. We have carbon here, which is graphite. All right? We have graphite inert electrodes. They don't react. All right? Graphite, they don't react. That's why we call them inert. This is going to be my anode because it's the positive, and this is going to be my cathode because it's the negative. Remember what we still have, Cu2 plus and Cl minus. Again, we have our migration quickly. This migrates towards the side, and this migrates towards that side. So that migration simply is a foundational reaction that will take place. Now, at the anode, I want us to see what we are going to have at the anode. Remember now we no longer have copper there, we have carbon. We have carbon electrode. So let me just do this. It's positive, and this is carbon, and we have what? Cl minus. Now, Cl minus is now here where carbon is, but we said carbon is inert. So there's no reaction with carbon there. We're only going to have Cl, and this is anode. Remember what takes place? At the anode, oxidation. Let's go and find out what our Cl looks like on our table. Chlorine. I think we found it a while ago. Where is chlorine? Remember, it's a positive value. Yes, right up there. But now we are going to have chloride ions being oxidized, because that's the one that moves towards our electrode. So we're going to have, if we copy that, this is what we'll have. Our half cell reaction therefore will be 2Cl minus. Remember, we copy and just change it around. Cl2 gas plus 2 electrons. So that means there'll be a gas actually given out here. And how do you know there is a gas? You have bubbles. That's a good place for a question there. You have bubbles. Bubbles tells you that a gas is being evolved. A gas evolved. Gas is being evolved. And what is the gas? It's our chlorine gas. All right. Now, what happens at the anode? Sorry, at the cathode, we have negative there, and we have Cu2 plus. Obviously, because this is the cathode, what we are going to have is what? Reduction. Cu2 plus again will be reduced to Cu solid. Again, we have a solid material being produced, which means there is a covering here. It's actually a brown covering. And here again, there is an increase in mass. However, on my anode, there is no change in the mass. I'm sure you know why. This is carbon and not copper. There is no change in mass. So, summary quickly, look at what's happening here. The carbon remains the same. The carbon remains the same. There is no change in mass, unlike the other one where there was a change in mass because we have a replacement of ion. So the concentration here, the concentration of our electrolyte, CuCl2, does what? Decreases. And what happens? It starts from blue color and it becomes light blue because the concentration of our Cu2 plus is now decreasing, light blue. And if it continues, it may just become colorless. Simply because our Cu2 plus concentration decreases. I needed to see the difference between using an inert electrode and using copper electrode. This is a good exam question where you could be asked about the concentration and to explain why. Here, as the concentration decreases, there is no replacement. But on the first one, so you might need to rewind and go through this first explanation where we had our copper electrode. Let me go back there. You see now, there's a decrease in mass, but remember that this Cu, I have it up there. So this is actually replacing what is lost. So that is a great difference between using copper electrodes and using graphite electrode. I hope we got that. So that's the first application of electrolysis, the electrolysis of copper to chloride. Number two, this is an industrial process now, electroplating. Electroplating. This is an industrial process. And why do we electroplate? First, let's understand what electroplating is. It is the covering of a metal with another metal. For what purpose? For better appearance. Probably for better appearance. All right. For example, maybe, with covering with silver, you could coat a spoon with silver for better appearance, increase economic value, to increase the economic economic value. And also for protective, some electroplating are done to protect precious metals, to protect the metals, probably from rust or something. So we have for better appearance, economic value, and to protect metals. Okay, I normally crack a joke in class to say people with gold tooth, if it was really a gold tooth, I would kidnap them. But it's really not a gold tooth. Okay, so I cannot kidnap them. It's an electroplated material. I want us to check something. If we are covering a material, let's electroplate a spoon. I want us to electroplate a spoon. Let's electroplate a spoon with silver. Since we want to electroplate a spoon with silver, we're looking at having solid silver. Since we want a solid to appear, therefore the spoon must be our cathode, because that is where reduction takes place. The spoon must be connected to the negative terminal of our battery. That is where reduction takes place. Remember, our aim is to have a solid material. We would see a diagram just now. I'm going to crop in a diagram here. Okay, let's check this diagram. And we would use this diagram. Good, we've got what I want. All right, look at this. We want to basically electroplate this iron spoon. Remember, iron rusts easily. It's an iron spoon, and we want to electroplate it with silver. Now check the terminals here. This is the negative electron, so this is the cathode. And this is my anode. Remember, electrons are still moving from the anode right through the cathode, because electron cathode is where reduction takes place. It's gained, and there is a loss of electron here representing oxidation, and we have our red cat. Now, since we are dealing with we want to cover this spoon with a silver metal, it's therefore necessary for us to have a silver salt. Now we have a silver nitrate salt here. Silver nitrate salt. Silver nitrate salt. Okay, silver nitrate salt. Remember, the steps actually remain the same. What will happen? You have your AgNO3 breaking down into Ag plus and NO3 minus. And here you have your silver electrode. So what happens? We have a migration again. The silver ions will move towards the spoon, while the NO3 ions, nitrate ions, would move towards the silver. So what do we have? We have at the anode, we have our nitrate, and at the cathode again, we have our silver. Let's see what's going to happen at the anode and at the cathode. We need a new page, so I'm going to separate the electrodes right now. Let's start with the spoon. Our spoon here is the negative. Remember, we have Ag plus, and this is what? Our cathode. And what happens at the cathode? Reduction takes place at the cathode. So we've got an iron spoon and a silver ion just close to it, connected to the negative terminal. Now the question again is, we've got two things here. We have Fe and Ag. We need to go back to our table and check which one is a stronger oxidizing and which one is a reducing. Okay, we've got silver here. That was quick. Positive 0.8. Let's write that value somewhere there. This is positive 0.08. Okay, And then let's look for iron. We should be dealing with iron 3. Iron 3, let's find it. Iron 3, here we are. Iron 3 is negative 0,06. Negative 0,06. All right. If you look at the table pointing up says increasing oxidizing ability, which means that our silver, let's get it, our silver is actually a stronger oxidizing agent than iron. Therefore, it will be reduced. So it will oxidize. It's the stronger oxidizing agent. Therefore, it will be reduced. Remember, we are at the cathode, and what happens at the cathode? Reduction takes place. So since this will be reduced, what are we going to have? We're going to have Ag gaining electron to become silver solid, and that's what we want, a solid material. Remember, this is aqueous. So our experiment actually works well. This spoon now will be covered with silver. Again, remember, there is an increase in mass. So we've electroplated the spoon. What will therefore happen at our anode? Again, let's try to separate it. At our anode, remember what we have. We've got silver here, and then we've got NO3 minus nitrate. Now, again, we need to go back to our table. Okay, what do we have on our table? Here we go. We have nitrate, and we have this. Okay, positive 0,96 and positive 0,8. This is positive 0,8, 0.8, and this is positive 0,96. This one should be reduced. The more positive will be reduced, while this one should be oxidized. Remember, we are at the anode, and what takes place? Oxidation. Therefore, our reaction becomes that of silver. So we have silver being oxidized to silver ions. What does that simply imply? There will be a decrease again in mass. There will be a decrease in mass because our silver solid is being oxidized to silver ions. And what happens to our concentration again? Just like we did the other time, our concentration remains the same. The concentration of AgNO3 will remain the same because NO3 remains in the reaction. We have silver coming in to form a new silver nitrate. As one mole of silver goes, another mole of silver just replaces. So the number of ions here remains the same. Hence, the concentration of the electrolyte remains the same until our anode, actually the electrode, all being oxidized into Ag+. That is only when the reaction stops. So this one would keep decreasing until it's finished. And once it's finished, it's an open circuit, our reaction just stops. So that is the electroplating. Remember, what you are electroplating should actually stay at the cathode, where reduction takes place. What you are electroplating should be at the cathode, where reduction does what? Take place. It's very important to have that in mind. The spoon should be at the cathode, where you want reduction to take place. That is the second application of electrolysis. It's quite simple since we spent time on the other one. Now, let's look at the third one quickly. The third one has to do with refining of metals. All right, refining of metals, the third one. It's called electrorefining. Metals are actually extracted as natural occurring elements, and they are actually in their ores. All metals are extracted as ores. What do we mean by an ore? An ore is just a mixture of metals. So in this case, let's work with an example of copper. If we have copper ore, if we have copper ore, it simply means that copper is mixed with so many other elements such as silver, you could have lead, you could have gold, and all other things right here with copper. So let's look at that quickly. Again, it's an electrolytic process. It's an electrolytic process. I'm going to probably play a video for us here again, but I need to do this explanation. Now, when we do this again, we have our electrode, but this time around we have to use copper electrode. DC supply again. Here we are going to have pure copper, because that's what we need. We need pure copper, and here you have impure. This is where you have the ore, and you would see why this has to be the impure just now. Impure copper. This is our anode, and this is our cathode, positive and negative. Simple understanding is we want to remove the copper from here and bring it there. So this is what we want to see. We want to see copper, therefore we need to put it at the cathode. So basically, can we say we see at C? That's Krazifizix already in action. We see at C. All right, we want to see copper. Remember, we wanted to see silver on the spoon, so we put it at C, at our cathode. We see at C. Good. And our electrolyte has to be a copper salt again. It's a copper salt. So we have Cu2 plus right in this place. We have copper salt. Let's use copper sulfate this time around, just to create a bit of difference, and we see what's going on. All right. Again, I think we must be able to predict what will happen now. Cu2 plus moves there. SO4 2 minus comes there. Already we've explained this. Cathode, the reaction of the cathode, the half cell, what happens? Cu2 plus, remember, it's being reduced. Let me write it here. Gaining electron on the cathode to become Cu. That's what you want to see. You want to see at C. But what will happen at the anode? What will happen at the anode? Okay, I wanted to see what will happen at the anode. Remember, at the anode we have impure, and then you have what? SO4 2 minus there. We have SO4 2 minus, and this is our impure. But remember, in here we've got Cu2 plus, so let's make this a big bowl of electrolyte, where we have our electrolysis process going on. Okay. Now, the impure here, since we have copper here now, all these metals would find a way of being dissolved into this solution. But copper will be oxidized into copper 2 plus. So we're going to have Cu being oxidized into copper 2 plus. Just looking at the reduction ability again and oxidation ability, with that we've been doing over and over again. So the copper solid will be oxidized into Cu2 plus, which goes back into the solution. While others, such as zinc and other impurities, would form what you call a sludge or an alloy, a sludge, which is the combination of other metals that are found here. So at the end of the day, we would have extracted copper by taking it into copper 2 plus, and then which moves towards the other electrode, and then it's converted back into copper. That is the same process, a simple process of our electrorefining of impure substances. So all metals are actually refined in such a way. And now we would look at that of aluminium. It's almost the same here, but there are a few things that will be added to aluminium. Again, aluminium will be extracted from its ore. But quickly, a quick recap on this. Remember, we have the ores, and the pure copper must be at the cathode because you want to see the impure one, which contains copper and other metals, comes to the anode. All other metals find themselves dissolving here, but copper, since we're dealing with copper 2 chloride, will find will be oxidized at the anode to form Cu2 plus, which goes back into the solution. So as long as it goes back into the solution, what happens? The concentration of the electrolyte remains the same, while the Cu2 plus now becomes reduced at the cathode to form copper. All right, so that's the third one. The fourth one. Remember, for all this, we still need to be able to write our cell reaction. In this case, there's no cell notation, but we still write all our half cell reactions, anode, cathode, and then we have the net ionic. The recovery of aluminium. All right, so let's deal with the electrolysis of aluminium. Remember again, aluminium, it's gotten from its ore, and the aluminium ore is called, now this is a good exam topic. The aluminium ore, which is where we get the original aluminium ore, is called bauxite. We need to know this name, bauxite. This is a good exam topic. It's called bauxite. So bauxite is extracted from the earth as its natural place where we get aluminium from. Now, this bauxite, there's a whole lot of process here. Bauxite contains, let's have this written down. This bauxite contains impure aluminium oxide. Impure aluminium oxide. And after this, the next session, oh my God, the next session would be to look at a whole lot of, we would look at activities just like we did aluminium oxide. Okay, it's going to be aluminium oxide, which is Al2O3. Now, so we said we extract aluminium ore, which is called bauxite, and it contains this. So we need to get our aluminium from this. Now, what is the first process after we have extracted? So this is what we extract naturally. I'll probably show you a diagram of what that looks like. I'll show you a diagram quickly of what that looks like after this explanation, so that the video also makes a lot of sense to you. Now, the bauxite is treated. Bauxite is treated with sodium hydroxide. With sodium hydroxide. And this is simply done to convert, this is the purpose, to convert the impure Al2O3, which is our, to aqueous alumina. to aqueous aluminium. Remember, we need an electrolyte, so this is what we're trying to get: hydroxide. And the formula of that is simply Al. Remember this, we did in grade 10 on how to write that. It's Al3 plus and OH minus. If we cross multiply there, we have Al and we have OH3 minus. Now, this one here has a name, and the name, in case an examiner wants to check your content, it's alumina. So bauxite is treated with sodium hydroxide to convert the impure aluminum oxide into aluminum hydroxide, which is called what? Alumina. All right? This alumina is now heated. All right? This alumina is now heated into purified. Now this one is converted to alumina, rather. Not this is aluminum hydroxide. This one is heated and converted into alumina. That's where alumina comes in. It's converted into alumina. So we have our impure Al2O3 being treated, and then we have aluminum hydroxide, and then this is heated to form alumina. And alumina, now this is pure. This is now, remember what we have: impure Al2O3, we have sodium hydroxide, and then we have pure alumina. So if I want to represent this in a flow chart, let's do this in a flow chart. Let's do this in the flow chart. What do we have? We have bauxite. And what happens to bauxite? Bauxite is treated with sodium hydroxide. And when it's treated with sodium hydroxide, what do we have? We have aluminum hydroxide, which is now heated. All right. Remember, this is your impure Al2O3. When this is heated, we now have your alumina, and alumina now is your pure Al2. Now, this is the summary of the process. So we've got bauxite, which is the ore, aluminum ore, treated with sodium hydroxide, all right, to form aluminum hydroxide. And this aluminum hydroxide is heated, and then you form pure aluminum oxide, which is called alumina. All right. Now, the process is not yet completed. It's quite long, but we're almost done with the process. Alumina. Now, what do we do with alumina? Now, I want you to notice, I want you to know that aluminum oxide, or your alumina, has a high boiling point. It has a high melting point, rather. It has a high melting point. Since it has a high melting point, what is the economic impact on that? We need a large amount of electricity. Actually, the melting point is over 2,000 degrees Celsius. This is very high. So this would consume a lot of electricity. In order to deal with this melting point issue, we now dissolve Al2O3 is dissolved in molten cryolite. It's dissolved in molten cryolite. The formula for that is Na3Al. It has a fluorine there. All right, molten cryolite. Simply because we want to decrease this melting point from 2,000 just to about 900 degrees Celsius, which is fair. So we bring down this melting point from 2000 just to about 900 degrees Celsius by dissolving this Al2O3 in chloride. Now, this mixture of Al2CO3 and chloride becomes our electrolyte. And let's see what the electrolytic process now. Now we want to go into our electrolytic process. What would it look like? The structure is a bit different and may be different as you move from textbook to textbook, but practically just the same. All right, we're going to have we will have that. This is connected to the positive terminal, and this container here is connected to the negative. These are graphites. All right, so we have graphite electrode. This becomes my anode. All right, and the container itself becomes the cathode. We need an outlet here. This becomes the cathode. Now, what we do now is this. We are going to have our electrolyte right in here. Remember now, plus, so we've got a series of graphite electrode. So we have Al2, let's use something different to write that. We have Al2O3. Remember, there's also chloride there. So we have this as our electrolytic setup, and this is called the Harald system, the Harald electrolytic process of aluminum. Now what's going to happen again? Now we go back to our normal processes. The Al2O3 aluminum oxide will break down into Al3 plus and oxygen. All right, O2 minus. So what do we have? Remember that the whole container here is negative. So we have our aluminum 3 plus attracted or migrating towards that, while the oxygen is attracted towards the positive graphite. So we have a migration again, same story as we've been talking about. Now what happens at the cathode? What do we have at the cathode? At the cathode, remember, it's reduction. And what do we have? Our cathode is positively charged. Our cathode is negatively charged. So we have our Al3 plus. So we're going to have Al3 plus plus 3 electron gaining to produce aluminum. And this is what we want. On the other end, at the anode, what do we have? We have oxygen and carbon. Remember, carbon is inert, it will not react. So oxygen will now be oxidized at the anode. And oxygen, you will have 0, 2, minus, and then we have, if you check your table, you would find oxygen that way there. And so we have that. Again, if we want to write our balanced reaction, remember what we've been doing so far? We need to multiply this by 4 and multiply this by 3 so that this becomes 4Al, 12 electrons, and 4. This becomes 6, and this becomes 3, and then this becomes 12. So that our final answer will be 4Al, 3 plus 6. You have oxygen there, and then you have 4Al. Can you see the end product? The end product is actually aluminum and carbon dioxide. So that's our redox reaction. The aluminum now it's taken off from here, all right, and taken into a container, allowed to cool and to solidify. This is the process. Now, finally on this, there are some important things we need to know. Oxygen is being produced at the anode. There's going to be a reaction. carbon dioxide gas will be produced. And this is a greenhouse gas. And this causes what? Global warming. So this process is quite complicated, and that's why it's good for exam purposes. All right. Still, the process uses a huge amount of electricity because of the melting point. All right. It uses a huge amount of electricity. Is that okay? By the way, we also need to keep replacing. We need to keep replacing the anode electrodes, because carbon is being, when we say carbon reacts with oxygen, actually it means it burns. So carbon is burning in oxygen, therefore it is used up. So we need to keep replacing. We need to keep replacing that electrode because it is being consumed by oxygen to form carbon. Remember, this is a gas. So you have the anode disappearing. So you need to keep replacing. You can keep replacing that. All right. Another impact on the environment will be that, remember the formula for cryolide. It has a fluorine, and fluorine is harmful to health. Fluorine is harmful to human health. Remember, we find fluorine in our cryolide. If I write down the formula of cryolide again, it is Na3Al F6. All right, so we have fluorine, which is harmful. So these are the impacts. Number one, carbon dioxide, it increases greenhouse warming, global warming. It's a greenhouse gas. We need to keep replacing that, which is costing. We use a huge amount of electricity, which is expensive. Fluorine, again, is harmful to health. Although, one of the positive things is aluminum products are easily recyclable. All right? Aluminum products are easily recyclable. Aluminum products are easily recyclable. So this is the extraction. Again, let's do a quick refresher course on this. All right, let's go back here. Okay, this was where we used so much of space. Now we said that aluminum is extracted by its ore, and the ore is called bauxite, and that is simply impure aluminum oxide. All right, to make it pure, we need to treat with sodium hydroxide, and because of that, we have aluminum what? Hydroxide. This is then heated. Already we're using electricity to produce pure aluminum hydroxide, which is aluminum. But this, again, we said, has a very high melting point, hence need to be dealt with by dissolving in cryolite. Again, we had this where the fluorine came in. We dissolve that in cryolite. This now becomes our electrolyte, and we have our setup like this. The container, the case of the container is the negative electrode, while you have rods here. These rods are the one that combines with oxygen, and they keep disappearing. So as the process goes on, this is what you have, disappears. As the process goes on, that's what you have, it disappears. As the process goes on, because carbon is combining with oxygen to produce carbon dioxide gas, a greenhouse gas. So you need to keep replacing. You need to keep replacing as the reaction goes on. Al2O3, again, we go back to our normal electrolytic process, breaks down into aluminum 3+, and O2 minus. Migration of these two, this moves to the negative, and this moves towards the positive, where oxidation and reduction takes place. At the cathode, what do we have? We have that reaction, and at the anode, we have that reaction. We need to balance by multiplying by 4, multiplying by 3. That we've been doing over and over again. And then we have this here as our final net reaction. That we have as our final net reaction. And these are the economic impacts. Carbon dioxide is produced, because we said carbon reacts with oxygen, and then we said we need to keep replacing that because this keeps burning. It burns in oxygen. We use a huge amount of electricity, and then we said fluorine produces fluorine, which is very harmful to human health. But all this said and done, aluminum products are easily recyclable. I'm sure that has helped us to understand quickly what we need to know about electrolysis. Let's try to see something interesting here, just to probably buttress what we've been talking about. All right. This is the extraction of aluminum, the Hall-Harrod process. Okay. Now this is all right. Let's go back just a little to see what goes on. Okay, I've done all this explanation here, but I want to go back. All right, this is our bauxite. This is the way it looks like. Bauxite ore. That's the way it looks like. Now it's been treated, and when it's treated, we have our aluminum oxide. All right, now we need to do that. Remember what we said, the temperature is about 2000. All right, so we need to use chloride, and we bring it down. It says below 1000, so approximately about 900 degrees Celsius, just to be able to bring down the melting point of aluminum oxide. This is a very important thing for us to know, chloride. Okay, this is just aluminum, being brought in from Brazil, Russia, for example, and we have our industrial plants where all this process takes place. The bauxite typically has small amount of other compounds present. Iron-3 oxide is present, and it gives the ore its brown color. All right, so iron-3 is what we want to really get, and that's where we get other materials are also present. The rock is crushed. Okay, the rock is crushed, the bauxite. We add sodium hydroxide. All right, that's what it's saying, alkali is added. And all the minerals are filtered off. Remember we said it's impure, we need to make it pure. And we have pure aluminum hydroxide. This is then heated to produce alumina. Just want to show you a picture of what the Hall-Harrod process actually looks like. All this explanation we actually explained. All right, now this is our setup. Okay, we have our anode, and we have the container, which is the cathode there. All right, the anodes are made from carbon, which is graphite. All right, it needs to be replaced regularly because it keeps combining with oxygen to form what? Carbon dioxide. That's the anode, the positive electrode. The container itself is lined with carbon, again, which becomes the cathode of this whole Hall-Harrod process. And we have the Al2CO3 just sliding inside. All right, our Al3 plus is attracted towards the negative electrode. Remember we talked about migration. We talked about migration of ions. That's the second process after the substances have broken up. Now carbon dioxide is given off because carbon combines with oxygen to form carbon dioxide. And that is as well, we said it needs to be replaced regularly. So we have our electrolyte right in here, all in here, our aluminum oxide right in here. And this is what the process simply looks like. It's a continuous process, all right? It's a continuous process that it keeps happening and happening until the reaction is complete. The reaction will be complete probably when we run out of carbon electrodes to use as the anode. All right, let's see what goes on that side. This side is now highlighted. Let's see what goes on that side. Okay, let's clean this just to make sure we have a good. That's the anode. All right, so we've got the anode here. Now look at this animation. Beautiful, beautiful. Electrons are moving from the anode, all right, back to the cathode. Remember, electrons are lost there, and this is what we have. 3 plus 3e to give us aluminum. That's what takes place at the cathode. That's reduction, and this is aluminum. The O2 ions are attracted towards the anode, and they are oxidized to oxygen, and that's where we have the oxygen coming together, reacting with the carbon to give us carbon dioxide. So the oxygen reacts with the carbon anodes, and that's why they need to be replaced all the time, making oxides of carbon. All right. So that is the process there of the hot anode, and this is how we get our aluminum. All right. Finally, and it's been a long session. It's been a long session. Is to deal with the chlor-alkali industry. Chlor-alkali industry, and this basically is the electrolysis. This is the last we're looking at on the session. Electrolysis of brine, and brine is concentrated sodium chloride. Concentrated sodium chloride. Like the ocean is actually a place that is very, very rich in sodium chloride. So we deal with the electrolysis of sodium chloride. Now we use a special kind of cell here, which is called the membrane cell. The membrane cell. Let's draw what the membrane cell looks like, and then we would analyze what goes on with the membrane cell. The membrane cell actually looks very, very easy cell to look at. Now the membrane cell is divided into two halves by what, and this is where it gets the name, by a cationic membrane. Cationic membrane, or what we call the membrane cell itself. It's cationic membrane. Now we have our electrodes here. Let me make this colorful for us. We have our electrodes, and obviously we remember that these electrodes will be connected to a DC supply. Since this is our positive, this is going to be our anode, and this is negative, this is going to be our cathode. All right, we've got, oh, by the way, we missed out something here. We've got two outlets. So we've got 3 outlets on the left and 3 outlets on the right. Now, we said this is electrolysis of sodium chloride. Now, we need to have a place where we are feeding the sodium chloride. The sodium chloride would actually come in, this outlet. It could be done, in a different way in your textbook or whatever resource you are using, but we feed in sodium chloride here, and here we have water. And this process is very, very interesting. We have water there. Now, what happens is this. The sodium chloride comes in here and breaks down again. We talk about its ions. And here, what do we have? We have hydrogen and hydroxide ion. So this is what we have. Breaks down. Now, what do you notice? This is our positive electrode, and this is our negative electrode. The positive sodium ions cannot be attracted to these. They need to find their way here, so they pass through our our membrane cell. I'm almost saying something like a life science. Our membrane cell, and then they are attracted towards the negative electrode. Why do we call this a cationic membrane? It only allows positive ions to pass through, cations. So the chloride ions are not going to be given a chance to go through, rather only the positive sodium ions. So they would find their way here, and then we have this. Is that okay? So we have that on that side. Out here, on this other side, we would see what's going to happen, and we would see what will happen here. So already we have our anode, and we have our cathode. Do you notice what's on the anode? The chloride ions are attracted towards these electrodes, while both sodium and hydrogen are attracted towards the negative electrode. Now let's break this electrode down. I hope that's simple enough for us to understand. Let's break this electrode down and see what happens. Positive, we have chloride ions there. Now what happens at the anode? It's simply oxidation, and what will happen? We're going to have at the anode 2Cl, all right, would give us chlorine gas plus 2. So chlorine gas is actually given off. That's why we have this outlet. I need us to feel this quickly. We have this outlet here. So chlorine gas escapes. It's produced there. Now, what happens at the cathode? What happens at the cathode? Remember what we have? We've got sodium, and we've got what? Hydrogen. But remember that the whole thing that comes in here is water. All right? So water is going to be reduced here, and when water is reduced, if you check the table, this is what we're going to have, 2H2O. Water would be reduced because that's what's first coming in, and then we have H2, hydrogen gas again, plus what? 2OH minus. I need us to get this reaction. Water is being fed. Let me go up quickly. Water is being fed in here. And we said it will produce this and this. But this comes from the fact that water is now reduced by this reaction. So hydrogen gas is given off, and we have our hydroxide ion also produced. So let's fill up that empty space again. I'm going to clean this one here. Now we are left with this. Remember that sodium also is here. So we are going to have a reaction between sodium and hydroxide ion to produce what? Sodium hydroxide. And on the side, we are going to be left with a less concentrated sodium chloride solution there. This is highly concentrated, or so let's just say concentrated sodium chloride going in, and here we're going to have what? Dilute, because not all the sodium chloride will be used up, so we have the remnant coming out of here. Very beautiful process, very, very lovely process. So first we have sodium chloride getting in here, breaks down into sodium and chlorine. The chloride ions are attracted towards that, and the sodium move through this cationic cell, which only allows positive ions to pass through. And here we have oxidation, and we produce what? Chlorine gas. On this other side, water comes in here. Water is reduced, and it produces hydrogen and what? OH. The hydrogen is given off as gas, and we have OH combining with the sodium that gets in here to produce sodium hydroxide. So if you look at this process, we've actually produced three things. We've produced chlorine, we've produced hydrogen, and we've produced what? Sodium hydroxide. Why, therefore, is this process very, very important? We are actually producing three things, and I'm going to be fast on this. We are producing hydrogen, we are producing chlorine gas, and we are also producing sodium hydroxide. Let's see, what is the importance of the cell? Now, let's start from each of these products. What is the importance of hydrogen? What is the importance of hydrogen? Hydrogen can be used in organic chemistry. In organic chemistry. Basically, we can use this in our organic chemistry to produce margarine. Get some bread right now. To produce margarine. It could also be used as rocket fuels. Your airplanes and whatnot use hydrogen because of its high combustibility power. Rocket fuels, all right, due to its explosive nature. So that's a very important element produced there. What about chlorine? Chlorine is used for water purification, grade 10. We learned that from grade 10. Water purification. It is also used as a bleaching agent. If you check all your bleaching materials, you have a bit of chlorine there. Your water purification, your swimming pools, it's used in cleaning water, all right, your bleaching agent. It is also used in organic chemistry to produce your polyvinyl chloride pipes. Your PVC pipes are the pipes we use in our houses. The pipes that takes water down through all the places. Your polyvinyl chloride pipes are also used in electrical wiring. PVC pipes. So chlorine is also very, very important. What about sodium hydroxide? Sodium hydroxide is basically called caustic soda, and it is used in the manufacture of soap. The manufacture of soap. Very important also. We use soap on a daily basis, and also can be used in the manufacture of paints. All right? Also in the manufacture of paints. Your paints are made from sodium. So you look at this. These three compounds, or these three elements produce, 2 elements and 1 compound, hydrogen, chlorine gas, and sodium hydroxide. All these compounds are very, very useful. Hydrogen, margarine, chlorine, water purification, the bleaching agent, PVC pipe, and your sodium hydroxide, manufacture of soap and manufacture of paint. Very, very important things. On the other hand, they've got their negative impact as well. Hydrogen, on the other hand, explosive. You talk about bombs, very flammable. All right? I mean, war, sizzling, a lot of hydrogen goes into use. Chlorine is very toxic to human lungs, toxic to human, very toxic to human. And that's why if you check on the packaging of your bleaching agent, they say do not consume. And here, this is corrosive and toxic as well. But more than their negative impact, they are useful daily, in our daily activities. I mean, first you wake up in the morning and you take a bath with pure water, clean water, and then you have breakfast, bread and margarine. Or before you do that, when you're taking your bath, you need soap. So you need soap from sodium hydroxide, you need water, and then you need margarine, and then you still need water again to have your tea, your coffee, and your daily life. So these these things are very, very important. This whole process is easy to run because why is it easy to run? Your electrodes are inert electrodes. These electrodes are inert, most especially graphite. They are inert electrodes. This system is environmentally friendly because all the products are very useful to human nature. Plus, this it's high, it's very purified sodium hydroxide that is produced, very purified. Unlike the aluminium process, where our electrodes are being used or burnt off, the electrodes here, we don't need to replace them, regularly, unlike the other one, because there's no reaction. I mean, chlorine and carbon will not react, hydrogen and carbon also will not react. So that is our process there. And this ends our electrolytic process. Remember where we started from? We did 5 things. We talked about copper chloride. First, we talked about copper chloride. You need to be able to make sure you get all this done. First, we talked about copper chloride, all right? And we used 2 things here. We said, what if we use copper electrodes and we used carbon electrodes? And then we talk about electroplating. When we talked about after electroplating, we talked about electrorefining. And then we mentioned the aluminium process, the bauxite and all. And then we talked about the chlor-alkali industry. I hope that this lesson, quite long, has been very, very helpful to you. In the next session, we'll be dealing with questions on this, just like we did on galvanic. We'll run about 10 different questions to make sure we get a good understanding. Once again, it's Bishop signing out here on behalf of Krazifizix. By the way, okay, don't shut me down yet. Don't shut me down yet. Let me do something crazy quickly. We did 2 cells. We did galvanic and we did electrolytic. All right, quickly. I want to show you something here. Electrolytic. It's elec. If I remove this L, what do I have? EEC. This simply tells me that, this is electrolytic. This is crazy now. My electrolytic cell would convert electrical energy to chemical. Electrical to chemical. While a galvanic will do the opposite, convert chemical to electrical. Okay, that's the first step. The second step is to reproduce our C. I'm going to write a C here, and I'm going to write an A here. This simply represents my cathode and my anode. Remember, when we do mathematics, it's always plus and minus. So I'm going to write plus and minus, simply because my cathode is the positive electrode here, while my anode is the negative electrode. Here under electrolytic, my anode is the positive electrode and my cathode is the negative electrode. Oxidation will always take place at the anode. Reduction takes place always at the cathode. Oxidation takes place at the anode. If you remember this, then you'll always be fine. Remember, you always see at C. All right, you always see at C. And also remember, if you're moving from the invisible close to the visible, it's reduction because you're reducing your level. All right, that's reduction. Your tables your table is written as a standard. Now this is just the crazy part. Standard reduction. And if you notice your table of standard reduction, electrons are written on the left side. So when they say what happens at the cathode, which is reduction, red cat, all you need to do is to copy what's on your table and paste. But you change that arrow into a single arrow. But if it is oxidation, what do? You copy, you reverse, and then you paste. All right. It's been a good class. Again, Bishop signs out here.